In this section of the discussion, we're going to talk about regularization, in which we introduce a new hyperparameter called alpha or lambda in order to penalize the complexity of our model and control overfitting. In the previous section of the discussion, we discussed the bias-variance trade-off, which states that as the complexity of my model increases, while the bias of my model will decrease, in general, the variance of my model will increase. So after some point, I get diminishing returns, in which while I get continually lower bias, the total error in my model starts to increase again, because the variance of my model is also increasing. So what does it mean to have a model that has a low bias but a high variance? Well, let's take a look at these graphs over here. Let's say I have a population in which there's a true linear relationship between x and y. Let's call that g of x. And so I take a couple samples from this population, and what I will get is that g of x plus or minus some noise. So I might get samples that look like this. And let's say I fit a linear model to the samples in my training data set, but I have features that are polynomial of higher degree, up to, let's say, degree 4. Then I will start to fit curves to the samples in my training dataset. And this model is an example of a model that has low bias and high variance. Why is that? Well, we see that when we fit these curves, they're going almost exactly through all of the points in my training dataset, which means that they're fitting the pattern pretty well, so they have a low bias. But we see that, for example, this model that we fit is quite different from this model that we fit. So the model has a high variance. It is sensitive to small changes in my training data set. It's basically fitting not only to the underlying pattern, it's also fitting to the noise. It's overfitting on my training data set. And that means that it is not going to generalize well. What do I mean by a high variance model does not generalize well? Well, let's say I generate a few more samples and I use that in my testing data set. Well, there's not a very high chance that that testing data set is going to have samples that look exactly like this or exactly like this. So if I'm going to fit a model on these kinds of training data set and try and use it on my testing data set, the testing accuracy is not going to be very good. And so how do I make sure that my model generalizes well? This is the motivation for regularization, which is a penalty on the complexity of my model. It's a penalty on the size of my parameters. I want to take these parameters in my linear model that correspond to these higher degree polynomial features, and I want to reduce them close to 0 so that they're pretty small. So I go back to a model that is similar to g of x, and that's going to generalize well to the population. And there are two ways of doing this parametric regularization. There's one called ridge regression and another one called lasso regression. And we're going to talk about these different types of regularization in the next part. Okay, let's talk about the different types of regularization. What happens when we have no regularization? Well, then we default back to our ordinary least squares, in which, of course, in our loss function, we simply want to minimize the average of our squared residuals. And we've already seen that the optimal vector of weights, if we use this method, is given by this expression, which we get by solving our normal equations. There are two types of regularization that we'll be seeing in this course. The first one is going to be ridge regression, in which in our loss function we have an extra term, which is alpha times the square of the L2 norm of our vector of weights. What does that mean? It means that I have an extra term, which is alpha times the sum of the individual squared weights. And that's how I'm going to penalize complexity. If I do that, then there's going to be a modification to my optimal solution, in which inside of my inverse, I'm going to have an extra term of n alpha times the identity matrix. It turns out that when we take the inverse of x transpose x plus n times alpha times I, we can actually ensure that this matrix is invertible. Adding this term ensures that that matrix is invertible. And so therefore, if we use ridge regression, we will always end up with an optimal solution. Finally, we have lasso regression. In lasso regression, we do also add an extra term, but instead of using the square of the L2 norm, we simply use the L1 norm of the vector of weights. What does that mean? It means I have an extra term of alpha times the sum of the absolute value of the individual weights. It turns out that if I use this type of regularization, then there's actually no analytical solution for my optimal vector of weights, and I'm going to have to solve it numerically. However, if I use lasso regression, it actually will set many of my weights in my vector of weights to 0. And so if I want to select only a few of the features as my important features, it might be useful to use lasso regression over ridge regression. Okay, so that's an overview of the different types of regularization. Now let's move on to answering the questions on the discussion worksheet. All right, let's go over the ridge and lasso regression portion of the discussion 10 worksheet. Here at the beginning of question 3, we have a lot of mathematical details about regression that I've already gone over. And we see that in regularization, we're choosing a specific regularization function that's called S of theta. And if we have S of theta using the square of the L2 norm, we have ridge regression. And if S of theta is using the L1 norm, we have lasso regression. So here we have a expression for the additional term used in ridge regression. And if this was a lasso regression, then it would be alpha times the sum from j equals 1 to d of the absolute value of each of the weights. So this is a lasso regression. And this is going to be ridge. Okay, let's go on to answering the questions. The first one is, as model complexity increases, what happens to the bias and variance of the model? So we drew the bias variance trade-off graph before. It looks like this. We have complexity increasing this way. This is variance. This is bias. And so as model complexity increases, we see that the bias will decrease and the variance will increase. Okay, what's next? In terms of bias and variance, how does a regularized model compare to ordinary least squares regression? Well, ordinary least squares regression does not have any regularization. And if we look at our bias variance graph, we see that complexity increases to the right, as we said. But since alpha, which tells us how much we're regularizing, penalizes complexity, alpha will basically try and move your model in this direction toward lower complexity. And so, this is B, this is B. If we're trying to go in towards the left, when we're doing regularization, then a regularized model will have higher bias and lower variance. Okay, in ridge regression, what happens when we set alpha equals 0? Well, if we have alpha equals 0, then there's no regularization, so this just becomes ordinary least squares. Well, if we have alpha to infinity, then we have infinite regularization, which means a huge penalty on all of our parameters. And so what will happen is that our vector of weights, theta, will go to 0. And so our model will predict 0 for any training data set that we throw at it. And this should be compatible with what we've discussed about bias variance so far. What will happen is that my bias will be maximized because our model's not very useful. It's just predicting 0 all the time. And our variance will go to 0 because our model is just doing the same thing. It's predicting 0 all the time because theta goes to 0. So that's what happens if we make a regularization really extreme. All right, how does model complexity compare between ridge regression and ordinary least squares regression? How does this change for large and small values of A? Alpha. So alpha is penalizing complexity. So ridge versus OLS. Ridge is less complex model. And we know that alpha is penalizing complexity. So alpha is inversely related to complexity. As I said many times before. So for large values of alpha, we will have an even less complex model. And for smaller values of alpha, we'll have slightly more complex model in ridge regression. Okay, part E. If we have a large number of features and we suspect that only a handful of them are useful, which type of regression would be more helpful? Well, we know that lasso sets several weights to 0. So lasso would be more useful. Finally, what are the benefits of using ridge regression? Well, if we look back at our solution, you see that the optimal vector of weights has this term in it that's guaranteed to be invertible. But while we don't have an analytical solution for lasso regression, so the benefit of using ridge regression is guaranteed solution. Guaranteed unique solution exists since this whole term of x transpose x plus n alpha I is an invertible. This is a big benefit of ridge regression, is that even if originally it wasn't solvable because x transpose x was not invertible, now you've made it invertible. So a guaranteed unique solution exists, and you've created that unique solution by imposing an additional constraint using regularization. And of course, ridge regression prevents overfitting. The whole point of regularization, since it's penalizing complexity and fixing your high variance model. All right, that's it.